Okay, let's look at practice question 1 for kinetics and doing questions that involve graphs. So the reaction between calcium carbonate and hydrochloric acid is shown below, and then you're given some amounts, some masses, volumes, and concentrations. So that on its own should sort of trigger that even if the question doesn't ask you to, you should be thinking about limiting reactants. You should be thinking about stoichiometry because they've given you these starting amounts. Now I've prompted you to do that here with question number 2, based on the given amounts, determine the limiting reactant. So you've got 10 grams of calcium carbonate, which is roughly 0.1 moles because it weighs 100 grams per mole. And then you've got HCl, which is a solution, and you've got N equals CV. And we've got a concentration of 1, and we've got a volume of 0.1. So we've also got 0.1 moles of HCl. So it would seem that they're matched until we look at the chemical equation and I see that I need 2 HCl's for every 1 calcium carbonate. And that means I'm going to use HCl twice as fast. And since I have the same moles, that means HCl is my limiting reactant. Now, even if they didn't ask me to do this, it's a good idea to think about this because as the amounts get changed in the question, you need to think about whether or not you've actually changed the moles of limiting reactant. If you increase the moles of something, but it's excess, then it won't have any impact on how much product you make. Okay, so sketch a curve to represent the data from the first trial. Okay, so they've given us the amounts, and I'm measuring volume of gas over time. I can see that volume of gas, that's based on a product, and so products increase over time. And so the general shape that we get in these types of questions in this type of experiment is something like this. It's a product, so it increases over time. It increases very quickly at first when there are a lot of reactant particles around, so very high frequency of collisions. And then as the reactants get used up, they don't collide as frequently, so the rate slows down, and eventually it plateaus when the rate finishes. So if we call this trial 1 in black, now we're going to show what happens when we make various changes. So in trial 2, I keep the same amount of calcium carbonate here, and I can see that I've decreased the volume of HCl, and I've kept the temperature the same and the concentration the same. So volume isn't really one of our collision theory factors. However, it does affect moles. And because HCl is the limiting reactant, if I make the moles go down, then I'm going to make the amount of product go down. And I can see that I've halved the moles, so I should basically half the amount of product that I make. So if I were to do this one, sort of a mark scheme answer would be that it should increase more or less at the same original rate because all of the rate factors are the same. We haven't changed surface area, we haven't changed concentration, we haven't changed temperature, and we haven't added a catalyst. So I'm going to increase at the same rate, but then I'm going to sort of trail off more quickly, and I would end roughly halfway compared to where the first one ended. So you're always in these questions thinking about two things, which is the end point, and end point I refer to as how high up or down, where's the y-axis endpoint? And that relates to the amount of product. So that's the stoichiometry part. That's where you have to consider limiting reactant and have the moles changed. The other part that's really important is the initial slope. An initial slope is based on rate of reaction. And how does rate of reaction compare between the trials? Okay, let me try to hurry up here. In the next one, it seems like everything is the same as the first trial, except the temperature has gone up. And we know that if temperature goes up, we're going to increase the rate of reaction, but obviously it doesn't change anything about the moles. So I need to make sure that I still end here, the same place as trial 1, but I need to go up more quickly. And so long as I do that, I'm going to be just fine on the mark scheme. Something like that. Okay, so that would be trial 3. Faster, same endpoint. Trial 4, it looks like we've increased the mass of the calcium carbonate. All other conditions are the same as the first trial. Now, calcium carbonate is excess, so if I increase the excess, there's no effect. So it still needs to end at the same place as in trial number 1. So that's kind of a trick that they'll try to throw at you. Now, we have increased the mass. It's possible that there, as a result, a little bit more surface area. So it might go slightly faster, but this isn't, unless you are given more information, you haven't really changed any of the traditional rate factors, things that would affect the collisions. So we'd probably want to just put it right along the same curve as the first trial. Again, you think about what's going to be on the mark scheme. I think that's what would be on the mark scheme. Okay, and 5. The original mass, let's see, what have we changed this time? Well, we've halved the volume, but we've also doubled the concentration. And that means the moles are the same of HCl, so we are going to end at the original spot, but we've doubled the concentration, and that means it's going to be faster, about twice as fast probably. So that means it's going to look a lot like the red trial, the higher temperature trial, which is it's faster, but equal moles, so same endpoint. And then let's see, there's a couple more questions down here. Trial 6, what would the curve look like if 100 cm cubed of water is added to the 100 cm cubed of HCl before mixing with the calcium carbonate? Well, by adding 100 cm cubed of water, you would dilute it. So adding this would make half the concentration, but equal moles. So I think it will look kind of like the, well, sorry, no, it doesn't look like any of these. It would go up more slowly, but it should eventually reach the same height, maybe over here, okay? So this would be number 6, because we've halved the concentration, that's slower, but actually the moles are the same. All I've done is add water, and therefore it's gonna be the same endpoint. Trial 7, what would a curve be like if 100 cm cubed of 0.5 molar is added to 100 cm cubed of 1 molar before mixing? Okay, this one's probably the trickiest of the bunch. In this one, I've added a bunch of acid that is less concentrated. So when I mix 1 molar and 0.5 molar, and I mix 100 cm cubed of both, you can figure out that on average, the new concentration will be right in the middle. Okay, so now I've got 0.75 molar. But I've got 200 cm cubed of it. And if you take the time to do the calculation, you'll see that you have increased the moles of HCl. So we've decreased the concentration of HCl because 0.75 molar is less concentrated than the 1 molar that we used in trial 1. Adding something that's 0.5 molar dilutes it, essentially. So we have a lower concentration, so it's going to be slower, but we've actually added more moles of hydrochloric acid. And so this one would be slower, maybe not quite as slow as the brown one. It would be kind of like somewhere in between, but it's also going to go past. And it doesn't really matter that you're super precise on that one, but it would be higher in the end. So slower, but actually a higher endpoint because we added additional acid, additional hydrochloric acid into the mix. And if we increase the moles of our limiting reactant, then we will see more product created.